Thank you. Thank you very much for the nice introduction. Well, I'm very glad to be here today and can tell you something about the 3D printing of hot work tool steel H11 1.2343. It is shown on the slide from the perspective of a self-printing injection molder. Now some people certainly ask themselves, what is a self-printing injection molder? And then also tool steel, even hot work tool steel. What motivates an injection molder to bring 3D printing of tool steel in-house? Well, actually, H&B Electronic is a manufacturer of electronic connectors. For almost 40 years, the development and manufacturing of plastic metal parts have been our core competence. The aim is always to bring some contacts into an injection-molded plastic part, either pressed into it or overmolded. What sets us apart is our high vertical range of manufacture. We work in such a way that we have, and we also want to have in-house, almost all the processes and technologies which are necessary to engineer and manufacture our products. The resulting deep holistic understanding enables us to offer sophisticated product and manufacturing solutions to our customers. We make our own tools and molds and manufacture other operating equipment internally. We have our own injection molding shop in which we use the injection molds we have built. In everything we do, we try to differentiate ourselves from our competitors by the most modern technologies and processes. And with this mindset, it is not unusual for us to bring a technology such as 3D metal printing in-house, to be able to produce mold inserts with near contour temperature control channels, and to expand our know-how in the direction of additive manufacturing. And that's why we jumped on the 3D printing wave and decided to establish and to expand metal 3D printing as another business unit. We deliberately chose a niche by selecting the material H11 and by purchasing a suitable machine from Trumpf. As a tool and mold maker, as well as a user of injection molds, we are convinced of the material H11. And we hope that we will be able to break down some barriers in a rather conservative industry with this material. The advantages offered by the use of mold cores with near contour temperature control channels has been known to us for many years. In the past, we've purchased these mold inserts as a service prints. And now I would firstly like to show you our main advantages why we use mold inserts with near contour temperature control channels. As you can see in the top left, with conventional manufacturing methods, you can only build a contour far temperature control circuit into the mold core. On the top right, you can see a solution. With tempering channel that runs close to the contour. Here, with a channel diameter of 1.5 millimeters, it was possible to penetrate into areas where the molding compound also gives up heat to the mold core. The comparative video of the simulation shows excellently how much more efficient the near contour temperature control channel dissipates the process heat which is introduced by the molten plastic. As a result, the part tempered near to the contour solidifies faster and can be demolded earlier. And this is what all injection molders actually know as the main reason for using conformal cooling. Actually, they should know. The shortening of cycle time is as a result of the faster heat dissipation is generally known as the main reason for the use of conformal cooling. As we will see, it is an important reason, but it's not the only reason. The example also shows how the heat removal from the melt can be homogenized by the channel guides. As you can see, a differentiation was made between the blue and the green channel cores. The two channel courses are not identical. Rather, the channel courses were matched to the plastic part. With it, it becomes possible to dissipate a lot of heat where a lot of heat is introduced by the plastic part. This increases the quality of the plastic part with regard to sink marks, warpage and shrinkage, for example. In the example, a shrinkage simulation showed us that without conformal cooling, the molded part would have been collapsed to such an extent that it could not have been used. So, conformal cooling can also make the impossible possible. The cycle time, and I can tell you, for us, reducing the cycle time has never been the main reason for the use of conformal cooling. With conformal cooling, we make the impossible possible, or we increase the quality of the molten plastics. The cycle time reduction is always included free of charge. And that's just as well, because the cycle time reduction will be needed as an economic justification for the use of 3D printed mold inserts. This brings us to an important part. Let's talk about the price. Compared to conventionally manufactured mold inserts, 3D printed mold inserts cost significant additional costs. If you will, the purchase of a bar or plate material is substituted by the purchase of a comparatively more expensive print blank. The molding core on the example cost additional costs of around 2,500 euros. The generated cycle time reduction was 4 seconds. That's 11.4%. The amortization calculation shows us that with this cycle time savings, the additional costs for the mold core were amortized in around 3 months. Well, and lifetime cycles, product lifetime cycles are still calculated in years. So the potential for savings is definitively there. So let's talk about the price again. On the one hand, we have the high price of the print blank, and on the other hand, we have the operation costs in production, where the cycle time savings brings improvement. And now, let me ask you a question. What is more important? The price for the print blank or the costs in production? Or maybe the operating costs in production are more important than the price. I hope the illusion worked, and on the first slide the price looks like a bit huger than the costs, and now the cost looks like a bit huger than the price. I can tell you both cards are the same size. However, for us as an injection molder, there's only one answer to this question, and this is not that both are equally important. Now we know that and why the cycle time savings are important for economic justification. As a family-owned Swabian company, we have something like economic justification in our blood. We Swabians are basically the epitome of saving money. And so, of course, we are striving to reduce the price that we just mentioned as not being so important because of the very fast amortization of the additional costs. So, of course, we asked us, is it possible to reduce the price? The answer is, yes, it is. It is characteristic for 3D printing that the print volume determines the printing time, and the printing time determines the printing costs. So, reducing the printing volume results in a reduction of the printing costs. But the question is how to reduce the print volume without changing the design of a part. Let's take a closer look at this mold core as an example. Here we have a mold core with a weight of 2 kilograms. If we print this volume, we will have a printing time of approximately 8 hours. If we look at the course of the temperature control channel, we notice that there are parts of the channel that initially run straight, and straight sections can be drilled. After these straight sections, the part of the channel begins which cannot be drilled. Basically, we can divide the volume of the mold core into 2 volume parts. Once in a volume fraction that can be produced conventionally, and twice in a volume fraction that needs to be 3D printed. The idea is now to produce a conventionally manufactured preform base plate onto which the volume that needs to be 3D printed can be printed on. Here you can see how this looks like in reality, because we have to attach the preform base plate to the printer's build platform. It is a little bit usual and has some screw-on options. The straight channel parts of the preform base plate are continued during printing, as you can see on the half-printed middle part on the right picture. You can have a closer look to these examples at the drum booth in Hall 12.0. Now let's have a look at a few numbers to find out what the volume reduction means in monetary terms. With the preform option, the print volume could be reduced by 50%. And by this volume reduction, the price reduction is almost 50% for this example. 50% cost reduction. That sounds good, doesn't it? And these 50% are not added before as a discount. So, finally, we can say it is possible to reduce the price of 3D printed parts by reducing the printing volume when it is possible to print on your preform base plate. Now, there are some people who say or ask themselves, is it safe to build on a preform base plate? Or do we get something like a predetermined breaking point, as it is known from processes such as vacuum soldering, for example? To answer this question, I've printed some test samples. I printed our H11 on an 1.2343 ESU grade base plate. Some test samples we have studied as printed and other ones after heat treatment. The test samples were separated. In the middle, the surfaces were grounded and etched to make the metal structure visible. In the first picture, you can see something like a dividing line. In the first pictures, you can see the results in the as printed state. The blue line shows the theoretical separation point. And on the first picture, you can see something like a dividing line, which lies a little bit deeper and shows how deep the laser melts the base material. The second picture, you can see in the right picture, you can see clear differences between the metal structures of the print volume and the ground material. So if we look at this, we have to say that it could be the case that there could be concerns about a predetermined breaking point, even if this is a material connection. So this looks not that good, but luckily we do a heat treatment, and after heat treatment the metal structures looks like this. Now you can see that you can hardly see any differences anymore. The dividing line has disappeared. There can no longer be concerns about a predetermined breaking point. Now this is one material. So, concerns destroyed. Unfortunately, time runs very fast here in Frankfurt. That's why I have to come to an end. That's why I'm leaving out the summary on this slide. I'm sure if you're interested, you can read it in the handout. there are also a bit more information that I could fit into the short time slot. And with this, I would like to thank you for your attention and wish you many more great expressions here in Frankfurt. Thank you.
Thank you, Thomas. Any questions? I can run the microphone out to you if you do. I had one question about so having the close contour channels, does that impact the life of the tool itself?
If you go too near to the tool wall, yes, it can. But if you choose the right diameter, or it will not have an impact to the lifetime.
And does it change the thermal cycling of the tool? Does it stay a more constant temperature through use, or you don't see the great temperature fluctuations?
We do not have any temperature fluctuations. We have more control about the heats in the tool. Yeah, that's what we have.
Yeah. Okay, perfect. Thank you.
Thank you.
Thank you very much. Thank you, everybody. Okay, our next presentation is from Martin Bock from Audi. He's going to be